To welcome Francois Ganachaud for an extraordinary seminar, I hope, in both senses. I'm happy to see so many of you here, even though it's not the normal seminar slot, and there are many PhD theses and seminars at the moment, so it's great that you came, but I must admit the title is promising. So Francois is a chemist, polymer chemist, working at the Laboratoire Ingénierie des Matériaux de Polymers à Lyon. He's known a lot for his work on silicones. More recently, also, he's done a lot of work on bicarbonates and interfaces. I think he will talk about that as well. And he works a lot on dispersed systems, emulsions, spontaneous or not. And I'm very happy that he accepted to share some of his know-how and knowledge and understanding of some of old modern questions today.
Thank you. I have a microphone. Thanks a lot for coming. I'm very happy to be here. I have to thank Wiebke to give me the opportunities to present this project that we work on for a long time, which is called the Ouzo effect. I've been presenting this everywhere, not in ICS, so it's the first time. I also, because Antonio is here and we've been working together, I will talk specifically about a specific aspect of this research, which concerns bicarbonates and ions and the fact that they stick at interfaces. Do you mind if I remove my, is it okay for you? No? Okay, I feel better now. Oof. Okay, so I titled it "Bridge Over Troubled Water," like the magnifique song of Simon and Garfunkel, because we try to put some bridges into this research, but there's a lot of troubled water below that, and many things that we actually don't really understand for a long time, and we keep on trying to understand things. So I'm not sure I'm going to be able to move. Can you come back? Just one second. Ok, merci. Okay. So hopefully I would be very delighted to show you these three parts, but I think I'm going to have time only for two. But if you have some questions on nano encapsulation, this is the main application of what we're doing actually. Most of the time I present it, but I prefer to stick on the second part, which is bicarbonate, because you may be interested, the physical chemist and physicist that you are here in the audience. Okay, so let's start with the beginning. What is the Ouzo effect? What is the physical chemistry behind this effect? What we want to do with the Ouzo effect is to make some emulsification. And you have many different ways to make some dispersions in water, nanodispersions especially. You can have high energy techniques where you smash things as much as you can until they get very small. So that's, for instance, what people do in the pharmaceutical industry to generate drugs of nano size. You can use low energy techniques by phase inversions or the Ouzo effect, and I come back to that in a minute. Or you can combine things. You can sonicate and evaporate solvent in the meantime to get some mechanical ways of dispersing things and some physical ways as well. So the Ouzo effect is in between, and it's very different from the other spontaneous emulsification techniques. Why is it called Ouzo effect? It's because of the Ouzo, the famous Greek beverage, and the equivalent, of course, is Pastis in France. But Pastis is very French, so when you go somewhere else and you try to talk about Pastis, nobody understands what it is. So that's why the guy who came up with this effect, who is American, used the terms of Ouzo, even if he was very fan of Pastis, actually. What is happening? When you add water in these beverages, you get an emulsion. And the perfect emulsion in the full volume, and you can see that it's pretty nice. And this is spontaneous, and that occurs in a second. It's very fast. The official name is emulsification by solvent shifting, but you have many other names. You have nanoprecipitation, which is used a lot. You have different ways of presenting this effect. And what is happening is it's very much depends on how you prepare things. If you have some oil and you add water and alcohol, you never get a chance to get an emulsion. On the other hand, if you put some oil in a mixture of water and alcohol and put some water in addition to this mixture on the right, you see that in certain conditions, you get a droplet dispersion. So what we have is a non-equilibrium system, which is not driven by thermodynamic, but which is some kind of kinetics process. The main features of the Ouzo effect, when you want to express how beautiful it is, you will say that it's spontaneous. It's only a few milliseconds to generate these emulsions. You don't need surfactants in some cases, in most of cases. So you can generate these droplets without the need for an external surfactant, even if you, at some point, you need to add it if you want to keep these droplets for a long time. It is simple and costs nothing. This is what you say to people in industry when you want to interest them. And then you put the drawbacks and the guys leave the room in a minute, because you said that it's very diluted. So the guys in the industry don't like it. You need to use a solvent, even if most of the solvents that we use are not that toxic. And there is a limited understanding of a process. And it's better now, but when we started, it was really far from being understood. What is really, really cool in this process is that you can emulsify almost everything you want, as long as the solute that you look at is not soluble in water. So you can start from polymers and you do what is called nanoprecipitation to generate some nanospheres of polymers, some polymersomes, some Janus particles. And here you have an example of some people who simply took a block copolymer that they put in THF, they add water, and depending on the conditions that they use, typically the content of THF and water, the time they take to generate this dispersion, the temperature at which they work, they are able to make small nanocolloids with internal structuration. And this is occurring very easily. They just play on some ripening to generate, for instance, at the beginning, some kind of bicontinuous structures that goes into lamellar ones when you wait enough to change the structuration of the system. You can start from lipids, and you can emulsify them and crystallize them, and you can generate liposomes or cubosomes if you want as well. This is an example here. You can start from solid molecules, and you will emulsify and crystallize them. So here I put an example of what we've done recently, where we use a fluorophore, which is very, very efficient when it's under a crystalline state. And by Ouzo effect, we've been able to generate first amorphous colloids and to transform them into crystalline nanocolloids. And you can see here, looking at the fluorescence, that between the amorphous phase and the crystalline phase, you get a very sharp increase into the fluorescence. So this is things that could be used in vivo, typically to make some imaging inside the body. And you can use reactive precursors and do some polymerization and so on. And in all cases, the only one compulsory condition to do that is that the solvent, the solute must be soluble in a given solvent, and the solvent has to be fully miscible with water. As long as you have that, this condition, you can emulsify whatever you want. So this is not that simple, actually, but the principle is simple. There is one very famous industrial application of this, BASF, not far from here, I guess, is precipitating beta-carotene, either synthetic one or natural one, into colloids of different sizes with different crystalline polymorph into these colloids. And depending on the type of aggregates that they make, the size of the object, they are able to range some colors from yellow to red using the same starting molecules. So they use that as dyes for food, especially for yogurts. So when you have a banana yogurts, you have a beta-carotene in, and when you have a strawberry yogurt is the same beta-carotene, but not into the same state. And it's pretty impressive the way they do that, because they actually have some colloids with crystalline objects into an amorphous matrix surrounded by gelatin, and that is prepared very fastly by a continuous system based on the Ouzo effect. Okay, so how does it work? I'm a chemist, I'm not a physicist, so I try to keep it as simple as I can to understand it. So basically what you have is here the yellow dots are your oil, for instance, into the solvent, and you add water. When you do is that when you add the water, you create a supersaturation. The water diffuses into the solvent diffuses into water, and the oil gets very bad into this mixture because it's not soluble. So it first generates nuclei, very small nuclei that aggregates together. And at some point, this aggregation stops and you get your emulsion. Bernard Caban worked a very long time ago about this process to precipitate some cholesteric molecules. And they showed by optical microscopy under very low supersaturation conditions that when you put a drop of solvent into a water surrounding, you effectively see the diffusion process, and you see that locally you precipitate things. In that case, because of the low supersaturation, you actually get small, big objects, but you actually are able simply by optical microscopy to see this effect. The emulsification is very fast. It's almost impossible to look at it. It's a few milliseconds. When you don't put surfactant in and you look at the size of the objects, you see that depending on the kind of solutes that you use, you don't get the same size range. You see on the left is an oil, a monomer, actually, divinyl benzene. So you see you have a micron size object, and if you precipitate polymers, you get much smaller sizes. But in all instances, what is happening is that in the system of nucleation and aggregation, you have some kind of stop event at some point where the nucleation, the aggregation stops, and the objects keep the same instead of aggregating until they phase separate. So you have some kind of surface poisoning at the surface of your object, and this is where we come back with the bicarbonate hypothesis later on. But what you see here already is that depending on the type of solutes, you don't have the same stop event, and you don't have the same size at the end. And you can the nucleation aggregation process is easily fitted with a Chomsky model that you have on the top, which says that basically the particle size or the volume size depends uniquely on the concentration of solutes that you have in your system at the beginning. And you see that the size is increasing with the concentration of solute that you introduce. And the size depends on the type of solute. And also, if you put some surfactant now, you see that depending on the kind of surfactant that you use, you can actually depress the size range, but you get the same evolution of size with concentration of your solute. So if you have oils with surfactant in the aqueous phase, the surfactant doesn't help really. So you have few micrometers. If you put the surfactant in the organic phase at the beginning, you get smaller size. And the best is if you take a polymer which has charges inside. In that case, you get 10 nanometers or less colloids made very simply by this process. And of course, you can combine them. And if I had time, I would have shown you that, but I won't. Okay, nanoprecipitation, Pastis is known for ages. Why is it that new? Why do we talk more now about that than before? It comes from the fact that Joe Katz in the US came up with some phase diagram to explain the system. And these phase diagrams were not known before, or almost not known before he came up with it. Here on the top, you have the ternary phase diagram where you have the water, the solvent, and the organic oil. You have the binodal curve, the spinodal curve, and the Ouzo effect is the Ouzo domain is somewhere in the middle. But actually, if you represent the phase diagram like that, you don't see it. So what he came up with was to change this ternary phase diagram into a binodal one. So you present the weight fraction of the solvent as a function of the weight fraction of the organic oil here. And you deduce the weight fraction of water from the other two, because the sum of the three make one, okay? So you go from a ternary to a binary diagram. And then what you do is that you expand the x-axis by putting a log scale. And when you do that, you start to see the Ouzo domain appearing. But you see that the range of concentration that we talk about is pretty small, is almost nothing. I mean, the best that you can get is 10 to the minus 2, 1% of organic oil dispersed into the system. But nevertheless, you have a domain, and you see that the limit here, what we call the Ouzo limit here, is very different from the spinodal curve, and the domain is very tiny. But it exists. And from that, it means that we can actually predict when we're going to emulsify things just by making this phase diagram. How do we do that? Very simple. I present here for hexadecan, for instance, an oil, very simple oil. To generate the binodal curve, you put hexadecan in acetone, you add water drop by drop, but at some point you get a cloud. And that means that you cross the binodal curve. So you go from a monophasic domain, homogeneous domain, to heterogeneous one. So this is very simple to do, this one. And then for the Ouzo limit, it's a little bit more tricky. And we came up recently, we didn't publish that yet, with an optical microscopy technique, where we look at different points of the state of the dispersion. And if we don't see nothing, that means that we have nanocolloids. And when we start to see things, we are outside of the Ouzo domain, we start to make to grow big droplets. And in that case, as you see here on the right, we shift from the Ouzo domain. And by doing that, you see that we can very elegantly, I would say, get the Ouzo domain here. It's for hexadecan, for instance, where we separate the emulsion, the true emulsion, with small droplets from the big ones. And we have checked by dynamic light scattering that we effectively generate in the Ouzo domain only small droplets without any big droplets surrounding the system. So what about Pastis then? This is the phase diagram of a Pastis, or an equivalent of Pastis. So it's ethanol, anethol, and water. And some people in, I think it's in Holland, came up with a phase diagram. And what you see here, so you start from the red dot here. And when you add water, you always end up on the Ouzo domain. So that means that you cannot fail a Pastis. No, nobody can fail a Pastis. That's a very important conclusion from this work, I think. Actually, you can fail a Pastis if you add so much water because the limit here is coming back here. So if you go very, very diluted, you actually have a demixture, but you have so few oil droplets that you don't see it. So you cannot really fail it. This Ouzo limit is not understood at the moment. We know that it can shift if we add surfactant or not. It's a sharp transition, and we don't know why. It can be linearized. We have some ways to linearize it. So it's a true limit. I think we could eventually explain it by some physics, but at the moment we don't. It depends on each solute and solvent. So that means that it's pretty painful because we have to make a new phase diagram every time we want to change the system. And it's a priori related to the chi component of each system. And at the time, we had worked with some physicists who had tried to fit the phase diagram for a polymer here, PMMA. And he was able, it was Jean-Pierre Cohen-Haddad who did this simulation, and we could more or less fit the Binodal. We could get a clue about the spinodal, but you can see here that the Ouzo limit was really not what was expected for the spinodal decomposition. So it remains to be explained. The other thing that is not understood is why do we get some kind of stable emission even if we don't have surfactants? So we know we have a system that are a priori charged negatively. The origin of metastability can be explained by two things. The fact that we have pretty big objects means that we don't have much post-value ripening, at least on short times. If we wait long enough, we do have some ripening and some coalescence. And we are very dilute, so the objects don't meet each other a lot. And because we have some charges, we can stabilize these objects. And so far, everybody in the community came up with the fact that hydroxide anion adsorbs on surface. And this is why we get negative charge. And this is why we stabilize these objects. And this is where we think that it's not correct. And I will show you now why we believe that hydroxide anion are not responsible for this negative charge. Bicarbonate may be the solution. By the way, I'm pretty open to every criticism at the end about that. That's why I'm presenting that here. You know, I'm sure you know that almost every interfaces around us are negatively charged. Hair, paper, textile, everything is negatively charged. Even at microscopic scales, when you look at bubbles, colloids, and so on, without surfactant, without nothing, most of the time you end up by looking at the charge is negative. And all surfaces that we talk about are in contact with air and water. It's been showed for a long time that if you look at zetametry, for instance, of some oil droplets here, it's the famous paper of Marinova quite some time ago in Longmire. And here it's another example, more recent, of the same type of emulsion. You actually have effectively a negative charge on the full range of pH, and the isoelectric point of the droplets are around pH 3. So there are three mainstream theories to explain that. So you have the hydroxide adsorption that many people believe is correct. And the idea behind that is to say, when water comes close to an interface, spontaneously, it separates into H plus or H minus. H minus stick at the interface and H plus leave the interface. Okay. And this on the full range of pH down to pH 3. Vacha and Rock more recently came up with the idea that it was not correct and that you have actually the other way around. It's positively charged and protons prefer interfaces. And you have Caban and a guy called Nate, I think in Germany, who said that we have impurities everywhere, like fatty acids, and these fatty acids can adsorb everywhere and stabilize the interfaces. And we propose another explanation, which would be that the bicarbonates and ions that we have around us could be responsible for that. Why do we come up with this proposition? When you look at the equilibrium of CO2 in water in a closed system, you see that basically on most of the pH that you look at, bicarbonates are the most present ions in a full range. At low pH, you can generate some acidic H2CO3, and you have carbonates at high pH. But the range that we look at generally in the middle is mainly composed of bicarbonate anions. And by the way, when you look at the concentration of H plus in red and OH minus in blue, they are also less present than bicarbonates in water. That's one first clue about that. When you look at the size of the ions and the charge on the ions, OH minus is a very hard ion with a charge that is localized very precisely on the ions here, whereas for the bicarbonate, the charge can navigate between the two CO, and the anions is big and is fat, and it's not that water soluble, by the way. So what we've done, because there's a lot of criticism and fights into this domain by the physicists, because most of the people who do experiments around that say that the guy who did the experiment did not work properly with not the right products, not the right conditions, and so on. So we try to work at the best as we can, working with products that we had purified and checked many times before we use them. We use three different techniques to try to show that bicarbonates could adsorb on surfaces that I show you now: interfacial tension, emulsification, nanoprecipitation, and freeze-thaw techniques. So this is the first example. When you look at so very simple experiments, and we didn't try to make things too complex. So you take a drop of water, very pure water, into hexadecan, or you do the other way around. You put a drop of hexadecan into water, and you look at the interfacial tension as a function of time. And you see that when you have the water in hexadecan, the interfacial tension does not change. Whereas on the other side, you do have a decrease of the interfacial tension as a function of time. So we explain that by the fact that in one case, you have very few bicarbonates into the water that can go at the interface. Whereas on the other side, when you have a lot of water, you have a lot of possibilities to absorb the bicarbonates. And it's driven by water, because if you put hexadecan in glycerol, ethanol, or in methanol, you don't see any change into interfacial tension. So it's only when you put hexadecan in water that you see this phenomenon. Nanoprecipitation, as I said before, we did some nanoprecipitation of polymers at different pHs, and we've seen that the size changes with pH, and that the best size that we get is in the middle, when we have an excess of bicarbonates anions. If we are too acidic, the size is increasing a lot, and it's the same case in the case of basic pH, where we're supposed to have a lot of OH minus to adsorb on the surface. And we check that it's not due to an increase of ionic strength, because we keep low into ionic strength in the conditions where we are here. And we did also these freeze-thaw experiments. If you take some a mixture of water and oil, you freeze it, you defreeze it, and you do that a few times. At the end, you get an emulsion spontaneously. And this phenomenon was not explained. And some people came up with the fact that when you freeze water, the CO2 that is inside is transformed into bicarbonates. So when you do that, compared to the original open air water, which is at low pH, when you do some freeze-thaw, you have the pH that goes back to 7, but the conductivity is increasing. Whereas if you purge water with a nitrogen, you also eliminate the CO2 because the pH is 7. But in that case, the conductivity is going down to almost 0 because you remove completely the CO2. So in the case where you freeze-thaw, you transform CO2 into bicarbonate. And when you do that, you see that as a function of the number of freeze-thaw that you make, the size of the droplets of oil decreases down to 5 microns here, simply because you accumulate some bicarbonates inside. And we effectively check that the pH is increasing with the number of freeze-thaw, the conductivity is increasing as expected. And we emulsify more hexadecan, even if the content of hexadecan that we emulsify is pretty low. So with these three measurements, we could say that, okay, we think that bicarbonates adsorbs on interfaces. Actually, the other ions also adsorbs, but less likely than bicarbonates. The more hydrophobic the surface, the more adsorption you get. And this is the case when you compare polymers to oil. Polymers adsorbs more bicarbonates than oil. And of course, depending on the content of CO2, you change the conditions, the content of bicarbonates, and you change the emulsification. So what we wanted to do next was to remove CO2 and see if we get the same. But it's almost impossible to do, very complicated to do. You would have to work into glove box. So we would have to put the interfacial tension measurements into a glove box. We don't have the capacity to do that at the moment. So what we've done is, instead of removing the CO2, we actually increased the content of CO2 and checked what was happening. For the nanoprecipitation technique, when we add bicarbonates, sodium bicarbonate, we see that the size of our particles is decreasing a little bit, but not much. But if we put too much of it, we have the size that increases again. And this is, we think it's because of ionic strength. The nanoprecipitation technique is not working very well when you have salt inside. Actually, the aggregation is preferred into a high ionic strength solution, but nevertheless, you see that we go down to diameters that we didn't have before. I've made a lot of experiments in my house with Pastis. It's very important to check on the real life what's happening. So what I've done is I took some soda stream water and I put that into a Pastis. And I waited one night and I looked at the result after 1 night. So on the left, you have plain water. So it's distilled water that I took at the lab. I soda stream it, some of it. And then I made a mixture. In the middle, you have half water, half soda stream water. And on the right, you have only soda stream water. So you have not to drink it, okay? So you just prepare it and then you leave it. And then you came the day after and you see that on the left, you have a full demixture of the Pastis. Whereas when you have CO2 inside and so some bicarbonates that are inside, you see that you actually keep some kind of colloidal stability into the system. So the fact that you have bicarbonates helps stabilizing droplets of anetal. I didn't try to drink it afterwards. And when you look at interfacial tension measurements, as I showed you before, the hexadecan drop into water in the atmosphere of CO2 in blue, you see that the decrease of interfacial tension is even more than you would get for the over atmosphere that you put. And for the freeze-thaw system, we use, again, soda stream water, distilled water, soda stream. And you see that even without any freeze-thaw, you already start with a very kind of nice emulsion with a very small droplets, 6 microns. It's almost what we get when we have non-soda stream water. And if you make some freeze-thaw again, you see that the size is decreasing. And you get an emulsion with droplets of less than 1 micron. So we believe that bicarbonates adsorbs on interfaces. This equilibrium is affected by a lot of different external systems. But in all cases, most of the time, we don't have enough of these ions to actually stabilize droplets or particles. So on the long term, you need surfactants anyway, if you want to get something stable. And these are the 2 papers that we made with Antonio about that. So I'm gonna, I think I'm done with the presentation. Yeah, I will go just to the conclusion, if I can. No, it doesn't work. Ah. Okay, thank you. These are the typical capsules that we can make with Ouzo effect. So conclusion, I really believe that Ouzo technique is pretty cool to emulsify almost everything. You can have a lot of different types of colloids formed. I didn't show it, but we can generate capsules with tags and trusses and everything we want inside on the top of the capsules and so on. There are very painful limitations. The one that is really painful is the dilution at which we are. We really would like to be more concentrated to get a chance to interest people from industry. And also the fact that we have to do a phase diagram systematically is a bit painful as well. So understanding better the Ouzo limit would allow to not do that systematically. So we are trying at the moment to shift the Ouzo limit. And we are looking for capsules that would not be cross-linked like we do actually with some nasty molecules. We want to work only with physical interactions to get nice capsules. So these are the people that I've been working with. I get a few money for that. And thank you for your.
Thank you very much.